Okay, so welcome. So this is our final, in one sense, a final lecture. So we're going to carry the last part of this statistical testing. So next week we will still have the lecture on Tuesday, in which we go through the main points of every topic that we discussed and have some questions and answers if needed. I'll record that one too. So just a very quick recap next week for the whole course. Last time, which was a week ago, we talked about hypothesis testing. And before that, we had talked about the confidence intervals. So hypothesis testing and confidence intervals have similarities to them. So you will notice that the formulas that we used are very much the same, and it's not a coincidence. The main idea of hypothesis testing, like we discussed last time, is that you formulate a null hypothesis in which you assume that the some conservative assumption is true, and you formulate the needed relevant distribution regarding what the null hypothesis is. Then you decide on the significance level or the risk level. Usually this would be 5%, 1%, or 0.1%. This is somewhat arbitrary, of course, but this marks the type 1 error probability. So we talked about the type 1 probability error, in which case the type 1 probability error, just very quick. Type 1 probability error is that we dispense or reject the null hypothesis, even though it should be true. So the conservative assumption is rejected, and the alternative hypothesis is accepted, even though the null hypothesis is true. So this is the probability that we can control. And here, the risk level gives you that if we assume, this is the curve here, the curve is for the null hypothesis. So this is the distribution, probability distribution that exhibited by the assumption that the null hypothesis is true. And in this case, if the null hypothesis is true, we see a distribution like this. And we opt for in one-tail test or two-tail test, depending on which we are talking about. If the alternative hypothesis is, for example, that the expected value or whatever the parameter that we're testing is smaller than the conservative estimate, then we define the critical region, and those would be those values that we might get that are improbable, uncharacteristically small. And the alpha probability, or the risk level, is the amount of probability mass here. So we are willing to tolerate this level of error. So if we get a result like this, these are uncommon enough to merit us saying that, okay, let's just say that this was not a fluke, because this was so, the probability of getting this result was so small. So last time I promised you the webcomic that discusses this, and I have to say this, let me just very quickly find out, what was it? It was, yeah, this is the one that I was talking about. So here's an example of the idea of the p-value being, or the significance level being 0.05. So there's this idea that someone claims that jelly beans cause acne. And scientists want to investigate, and then they say, we found no link between jelly beans and acne, with p being greater than 0.05. That means that we don't find, it's not in the critical region. So the relationship, you take people with acne, the probability of getting acne is higher if you eat jelly beans. Is it or is it not? So you get these two alternative hypotheses. So the hypothesis would be that the prevalence or the probability of getting acne is the same with or without jelly beans. And if the results differ with p-value greater than 0.05, sorry, the p-value is greater than 0.05, we conclude that there is no link. And then here's an idea that they test with different colors like purple, brown, pink, blue, teal, salmon, red, whatnots. And then there's this one. We found a link between green jelly beans and acne, p smaller than 0.05. So if you're careful, you see there's 20 panels here, but 1 in 20 on average will produce, you know, if you do many enough of these tests, then 1 in 20 on average will provide you with a critical result that is in the critical region, even though there is no difference. This is just going back to this picture. So you take values. So most common values will be here, but then, you know, if this is 0.05, for instance, then 1 in 20 results will be in this critical region regardless. So that's the idea of the probability of type 1 error. So that's your type 1 error, 1 in 20, 1 in 100, or 1 in 1,000. The probability of this is that this probability denotes the probability that you get a result that is like this, even though the null hypothesis is true. And if you put this to a very small one, then you have a very small probability of, this is the probability of you accepting the alternative hypothesis, even though the null hypothesis is true. The problem is that we don't know the probability of the null hypothesis being true. The null hypothesis itself can be false. It's either true or false. If the alternative hypothesis is true, you know, what can we say? We can say nothing about that. The only thing we can say is that if you increase the sample size, then both probabilities should go down, and if one probability goes up, the other goes down, and vice versa. All right. So the process is such that after choosing the significance levels, you choose the test statistics, which means that this is the test variable that you test. You come up with its distribution, assuming that H0 is true, and calculate the value from the sample. And then you calculate the p-value. If this p-value is in the critical region, if your value is in the critical region or p is smaller than alpha, then you reject your null hypothesis. Otherwise, the null hypothesis stands as it is. I'm sorry for my yawning. So we talked about testing the expected value a little bit. There were some typos here. I did fix them in one version, but this one I didn't upload yet. Let me revert to the one, I'm going to revert to the one that I have on my laptop, because it's better. All right, and now let's get down to business here. All right, so we talked about testing the expected value, and the idea of expected value testing is that we come up with the probability measure. So sorry, not a probability measure. We come up with the test statistics that has, in this case, the 0-1 test normal distribution, and this is called the Z. And very easily, if we have a sample, then the sample average is very easily the sample mean has the same expected value as the original variable. You take a large sample of it, and the variance goes down. So in particular, you get this normalized variable Z, which is the x bar minus mu 0 over sigma over square root of n. So this would be 0-1, a distributed variable. This is just the same value as we calculated when we calculate the confidence intervals. We use the same idea in confidence intervals. So we don't have to take the interval now, generate the interval now. We can just calculate it. Or we can calculate the interval and we can come up with the critical region, and that's the region outside the confidence interval. So it's the same thing as the expected value test in this case. And we have this table that if we're testing, if the alternative hypothesis is that our expected value has gone down, then the region, the critical region is the tail, the negative tail of the distribution, and we get the b value from the normal distribution. This z here is the actual value. Pay attention to this fact here. This is the defined random variable, but when we have the lowercase z, it means we take it from the actual sample. In actual sample, the lowercase value. And then we get the p-value as this. If it's if the alternative hypothesis is the one tail, the high tail, you know, the larger values tail, so we get a value that is above that limit, and then we get 1 minus z, you know, the value at the cumulative distribution function at z. And then if it's just that they're different, then we have these two tails. We have the half of the probability mass at the negative and half at the positive end of the distributions. And then the p-value is whichever p-value we get. I mean, if it's a small, it's this. If it's large, it's this value. And now, otherwise, if we don't get any of these values, or if the p-value is not smaller than alpha, then we do not reject the null hypothesis. That's the idea. So here was an example of the annual rainfall. I skipped that. For Friday, I have a few of these examples again. We'll talk about those. I put them online, and I can go through these examples as well there. So the central Riemann theorem implies that the larger samples, this sample mean is approximately normally distributed itself, even though x is a. So this means that this method can be used if the variables are not normally distributed, as long as the sample size is very large and there's no fishy, pathological, weird distributions going on here, the ones that don't have expected value, for example. So if the variable doesn't have a expected value, then this doesn't apply, of course. So this was when we knew the variance, but if we don't, usually we don't know the variance. Here we have the same thing as we had with the unknown variance in the case of calculating the confidence intervals. We calculate the t statistics, or this t distributed. It's just like that. Instead, we use the s here, which is the sample variance, and we test it against a positive, or the hypothesized null hypothesis expected value. But here we use the t distribution n-1. We can compare this to the critical value exactly like in the known variance case. So factory states here, it was an example of vowels and 5% chance should it be shipped forward. We calculated that a little bit by hand. Equality of expected values. There are some things that we have to discuss. Firstly, if we know the actual variances, in this case, if we know the variances of x and y, but we don't know the expected values, we have to determine whether they have the same expected value with known variances. The variances can be different, but we have to know them. So we come up with this statistics, which is simply the difference of the averages. And we know that if these are assumed to be normally distributed with known variance and known, unknown expected value, then this statistics will have expected value of mu x minus mu y, of course, the difference of the expected values. And because of the normality assumption, the variance is simply the sum of these variances, because it's these are normally distributed, and this is still normally distributed. This assumes that they are normal distributed. So at n and m don't have to be the same, and so forth. And we can come up with the test statistics easily. This is just your z variable, your normalized normal distribution variable, whereby we just take the square root of the variance, which we know here, and divide this. So in here, if we assume that these are the same, then this would be 0, and also the expected value of this difference of this sample means is also 0. This is under the assumption of the null hypothesis. I mean, if the null hypothesis is false, then obviously this is not 0, 1 normally distributed, because this one here doesn't have a 0 expected value. If variances are unknown, but we can assume them to be equal, then we can combine the sample variance into one big sample variance like this. So if you look at the sample variance of x, so you add you add the terms in that. So what you get is this, the sample variance. Let me just have a piece of paper and write it. So you have your S of x is equal to the sum from ranges from I8 ranges from 1 to n. Sorry, S squares, x I minus x. So this is your sample variance for x. And then for y, there's 1 over n there, of n minus 1. And then that's 1 over m minus 1 sum as I ranges from 1 to m y I minus. So you have these two, right? Now, if you combine these two, then assuming these sample averages are roughly the same, you can come up with a combined sample variance, because you can assume that the variances are the same. This is an unbiased estimate of this variance of both. And in this case, we can get this test statistics like this. We have the fixed or the combined sample variance, and then the sample variance of this can be estimated as this and estimated as that, and this turns out to be Tn plus m minus 2. So you see here, this is a little bit complicated. We'll look at some examples and some exercises in order to do this. I'm not going to go in depth into the theory of why we can do this, but the problem comes from the situation where the variances are unknown and different. And in that case, I'm not going to tell you how to do that, because it goes far beyond what we're dealing with here. It very quickly gets very complicated. So here's a warning for you and something to understand. When we make these assumptions, there were heavy assumptions here. For instance, in one part, we assumed that these expected values, when we are testing for them, then the variances are known in this case. In that case, we can calculate the test statistics pretty directly. In the other case, we didn't know the variances, but we assumed that they are equal, in which case we can use the information from both of these and combine them in such a way to get the t statistics. It's tempting to use this formula and replace this variance and these variances here with sample variances of x and y. The problem is the sample variances of X and Y have a chi-squared, kind of like chi-squared distributions. Not quite, you have to divide it by the actual variance. And the problem is that if you don't know these, then what you get here is if you have the same, if you have this as an estimate of the of the actual known variance of both, then this becomes a unbiased estimate of both of their variances here. But if you have to replace this with the sample variance of X and this with the sample variance of Y, then the resulting test statistics will not have a t-distribution, and that's the problem. If the variances are different, then the result is not t-distributed, not like this. And the theory of how to fix that gets quite complicated and falls out of scope here. So you understand that the limits of what we can do with the machinery we have now we've already arrived at there. So we can't really deduce more. Even as it stands, people still do it. People still calculate it, but it's wrong because you get overtly optimistic results. You get narrower confidence intervals, and you get results like this is significant or the null hypothesis is rejected. You get a p-value of 0.01 or something like this, when in fact that result could just be a fluke because the variances are in fact different. So that's something you have to understand. So if the variances are known, fine. If they're not known, but we can assume that the variances are the same, fine. But if variances are both unknown and different, then we can't use this directly. And we don't have a formula here for that. So please understand that falls out of scope for the limitations of what we can do now. So here's another example. Assume that we have this X, which has this distribution mu of X, unknown, of course, and sigma squared, unknown, but whatever it is sigma squared, and Y has the same variance and an unknown expected value. And we have these samples X and Y, and we have to test the hypothesis pair of equality of the expected values. So let's do that now. We have time. So I'm going to start my MATLAB, and I'm going to show you there. Just a second, takes a little while. All right, now you can see my MATLAB window here, I hope. All right. So let me just check the numbers from there. I hope you can view in an alternative window the slides so that you can keep looking at that. So I'm going to punch in these numbers. So my X is 4.1, 4.2, 4.8, 4.6, and 4.9. My Y is 3.9, 5.1, 4.4, 4.2. All right. So we do not know the variances, but we can calculate the variances of the sample variances of X and Y. And for, of course, we have the so we have the sample mean for X, and I'm going to have bar Y as mean Y, sample mean for Y. Just have to check. I'll have to check the help for the what's the variance? Is it just var? Yeah. Okay, so we have the variance of X, variance of Y. All right, good. So this would be, I'm just gonna say right here, oh, sorry. So S2X is the variance of X, S2Y is the variance of Y, right? And now I'm going to calculate the, so let's just, no, what was the, oh yeah. So I just write n equals 5 and yeah, m equals 4, right? So now I'm going to calculate the test statistics. Sorry, first calculate the SSS2. And that would be now my n-1 times S2X plus, I'm going to put here parentheses, plus m-1 times S2Y, right? Divided by n plus m minus 2. And that's my combined sample variance there. And now my t statistic is bar X minus bar Y as is. And I do it like this so that you understand what I'm, oh, sorry, times, sorry, divided by the square root of S2 over n plus S2 over m. That's my t statistic, okay? So this is my t statistics, and I'm now going to calculate and my n plus m minus 2. Oh, sorry. Yeah, no, that cannot be true. I'll have to cheat. I'll have to cheat a little bit. Let me just go back to the sorry, not t in row. Okay, let me just, I'll have to draw a picture. So here's my t distribution, I get a t value. I need to get yeah, sorry, that's the was it TCDF? Yeah, TCDF T, sorry, I was thinking the wrong way around, n plus m minus 2, that's my. So the cumulative distribution function, that gives the probability of we have a probability of 65% of getting a value as big as this t. So we are getting this, right? So this is a larger than 0, so I actually calculate 1 minus that. So that's my p-value there. It's 34%. So we're not going to be rejecting the null hypothesis here. It means that we will now conclude that the test gives us that the null hypothesis remains. They have the same, well, we can conclude for sure that they have the same expected value, but what we can conclude is that this is not terribly unlikely as a result if we calculate the expected values, right? So whereas the x's average is a bit higher than the average of y, assuming that they have the same variances, then the probability of getting a result such as this is about 34%. So it's not that unlikely. So in about 1 in 3, we get a result that gives, with a sample like this, we get a result where one is bigger than the other. Okay. We're going to go through these examples in a bit more detail during this. So sorry, I was calculating the wrong way around. Of course, it's the TCDF. That's the p-value there that I calculated. So all right. On Friday, we'll cover these in a little bit more detail on how to calculate these. We have an example of each of these type of things, and we can calculate. I can show you this these examples that are in these slides. I really do urge you to go through these examples that we have on Friday to over the weekend, and I'll show you. I can show you some of the. I think I'll add some examples today or tomorrow for you to study before Friday. All right, let's go. The other thing that we can test is a hypothesis regarding variance. So now if we have a sample where we do not know the expected value or the variance, we know neither of these. And the null hypothesis is that we have certain variance that somehow we've established. So let's, for instance, say that let's just say that we have some reason to believe that maybe some machine is wobbling a little bit more. So maybe let me say the situation is such that we are measuring something where the expected value is less important than the variance. And we have some established limits or some established variance that is tolerated. So it can vary a little bit, but not too much. And we want to check whether the variances remain the same. So recall that we can come up with a chi-squared distribution when we know the sample variance S, capital S squared. Then normalizing that, we get a chi-squared variable by dividing it with the actual variance, multiplying by n-1, because this is the sum of these zero. Well, you can think of this as having a sum of 0, 1 normally distributed variables. This left-hand side, and we can test statistics if this is in fact the actual variance, this sigma 0, then this will be chi-squared distributed. And now we can test whether this is now we have an empirical value, which is this S squared, and we have the hypothesized value, which is this sigma squared. And now what we can do is we have a distribution for this test statistic. If this null hypothesis is true, then it should follow this distribution, and then we can find a critical region here. So we can do this exactly the same way as determining the confidence interval. Remember the confidence interval? We calculated the same statistics and we divided, solved this for this sigma. So we, in that case, we solved the sigma. Sigma was at the center, and we calculated from the this empirical value. We got these limits of the confidence interval. This is just the same thing, except now we are trying to determine whether the result is in the critical region. There's a, oh, sorry, there's a slight error there. So we do the same calculation here, and I'm just going to write by hand. So we have here that the W is equal to n minus 1 times S squared over sigma squared, sigma 0 squared. So this is our test statistics here. So if we have a distribution under this assumption, and I'm just going to draw that it looks something like this. So this would be your chi-squared distribution. And if you want to test whether this value is if you want to test whether this value is small, then you get this region here. If you want to test whether it's large, you have this region here. And if you want to test whether it's simply different, well, the combined probability in this and this region should be the amount of alpha. It says alpha here. That should actually, technically speaking, be alpha divided by 2. And that should be alpha divided by 2, because when you're testing the hypothesis of difference and you don't know whether you're going to hypothesize whether it's bigger or smaller, then you have to have half your probability in the big values and half in the large value, small values. That is because you don't know which one it will be, right? Sorry, there's a V here, it should be W, so I'm just. So, okay, this is already a little bit bad because we don't have the, I should probably update this a little bit. It's not very good for self-study because I omitted the formula here. So let's go back to calculating the intervals there. And I'm going to do this using MATLAB. I'm terribly sorry that I'm going to do this. I'm going to just switch to MATLAB, and I'm going to show you how to do this with MATLAB. Okay. And just a second. So you're seeing a MATLAB window now? Good. Just 1 second. I'm going to. So we're going to do the variance testing here. So we're going to calculate the test statistics as per the example. So I'm just going to move this a little bit so that we can. All right. So our values for X were given as 453, 460, 351, 421, 339, 439, 402, 422, 470, 310, 416. And we are asked to calculate it with 1%. And our null hypothesis was that sigma 0 is 1100. That's our null hypothesis. And now we have to calculate the W. So remember the variance of X, we calculate, that's our S squared. So our W is, oh, how many X's? I'm just gonna have here. So N equals 11, right? So our W is now N minus 1 times the variance of X divided by this, well, sigma 0, that should be sigma squared, or sorry, sigma 0, that should be sigma 0 squared, but that's, you know. So this is our test statistics. So we have to calculate the value of where this is. There are two possible ways. We can calculate the cumulative distribution function at n-1 of this. So we get then we get the p-value. So to CDF. So I'm just going to explain here that, just draw a picture what we did here. So this is our assumption is that our W should have some distribution like this. And we got this result 25.1007. I have no idea where this is. It's somewhere in here. It could be here, it could be there. I have no idea where it is. And I'm going to calculate this cumulative distribution function at this 25.1007 and n-1. That's how probable all the stuff on the left-hand side of this value are. So it's 0. So it gives that the probability here is 0.9948. So really, I want 1 minus this. I get 0.052. That's my p-value. So my p-value is now less than 0.01, and I conclude that the null hypothesis is rejected. Alternatively, I could determine the critical region. And how do I calculate the critical region? In my question, in that question, it said, here, as we have previously determined that this variance is 1100, and we want to check whether the variance has actually changed. So we need to calculate the critical region here. And we want to check whether it's changed. And well, honestly, the variance seems a bit big, doesn't it? I mean, if you look at this bar variance of X, it seems a bit big. It was supposed to be 1100. This seems to be big. So if it's changed, it's probably grown. So let's take the null hypothesis as whether or not it's grown. Is this too big? So I'm going to just calculate the critical region. And how do we calculate the 1% critical region? Well, because this is a big value, then we are going to look at those values that have this 1 minus alpha. So 1 minus alpha, and alpha was given at 0.01 and n-1. So if I get a value greater than this, then I would expect it to be changed. This is my alternative way of doing this. This is the critical region. So I determined here that, I'm going to delete this, edit this picture of mine. So I now determine that this is my W alpha. this is my W alpha now. This is the value that I just calculated, that because this key inf that W alpha is that's my critical regions limit. So for the large value, okay. So I get here, this is my W alpha. So this value is 23.201. And I now look at that again, the W. This is my test statistics, and my test statistic is greater than this. So it's somewhere in here. So I conclude that the zero hypothesis or null hypothesis is wrong. Well, I reject the null hypothesis because this was a value far greater than this critical value that I determined. So this is not, it's not overtly complicated, but it may require a little bit of thinking. So that's why I will compile a little bit. I mean, there were examples, but I think I have to compile a little bit more examples because it's non-trivial for people for whom this is a new topic. Let's carry on. So this is fairly easy still. So the problem is that often what we need to determine is are two variances equal? So we have two samples and they have possibly different variances. And we have to check whether they are equal. And the problem is that the sample variances will have chi-squared distributions, right? If we start subtracting them, then if the n is very large and one of them has an m that is really small, then we could have something that looks somewhat like a chi-squared distribution with n minus m. But if both n and m are large, then it's not going to look anything like a chi-squared distribution. So we need another distribution. This is just for reference here. And I don't want you even to look at this formula. This density function of what we say the F distribution is totally not needed. What happens here really, what happens here really is that this approaches again when both n and m, sorry, n1 and n2 grow to be relatively large, then this approaches normal distribution in a way, but that doesn't really. I don't want you to think about what this probability looks like too much. This is meant to capture the idea that if we have a proportion of two chi-squared variables, so it's going to be a very wide and strange looking distribution, and don't have to worry about it too much. So we have two parameters here. It doesn't have just one parameter. It has two parameters, n1 and n2. These will be the sample sizes of your, well, almost n minus 1 and m minus 1. This would be closely almost the sample sizes of your tests. There are some tables or software such as MATLAB that allows you to calculate the cumulative distribution function of this F distribution. We're going to be needing it. And the F distribution has this symmetry that, that F with parameters n1 and n2 is the inverse of F with n2 and n1. So if n1 and n2 are the same, then F and 1 over F have in fact the same distribution. It's relatively weird. And this has the consequence that if we have the probability that F is smaller than X, it's the same as the probability that 1 over F is greater than or equal to 1 over X. So it has this symmetry around the value 1, if you want to think about it like this. And the important part here is that really, if we have two chi-squared independently chi-squared distributed variables, then their proportion or their normalized proportion with respect to n1 and n2 is F's distributed. So this gives us a test statistics. If we have two samples, X and Y, where X is normally distributed and Y is normally distributed, then the normalized, well, the sample variance of X divided by the actual variance of X, and then that divided by the sample variance of Y divided by the actual variance of Y, has the F distribution n-1, n-1. So this is the important part here. So we can derive a distribution for this sample variance, normalized sample variances, when the normalized sample variances are chi-squared distributed, but yeah. So we can derive it straight from this theorem that states that it's like this. Then we can come up with this by noticing that we can normalize this by n-1, n-1, and this by n-1. And in particular, if we have the fact that this variances are the same, then if the variances happen to be the same, then the sample variance of X divided by the sample variance of Y follows the F distribution with n-1, n-1. So it's the proportion of the sample variances that have this F distribution if these variances are the same. And that's the way we can test sameness of variances. So we can fairly easily calculate this. If we can come up with this test. This is now a test statistics, directly the test statistics for testing the sample variances, for the sameness of variances. We come up with this, we calculate the proportion of the sample variances. And then we determine the critical region from F distribution. If this value is very small, then this variance of X is probably smaller than the variance of Y. If this proportion is very large, it means that probably the sample variance of X, the variance of X is probably larger than the variance of Y. And here we have these regions. So if for the small values, X has a smaller variance. For the large values, X has a larger variance. And if we just test whether they are different, we have the very small values and the very large values, and then we can determine this. So here's again a question. We have a course has 51 students, and the number of points as sample variance 478. Another course has the same exam, but only 26 students, but the sample variance there is 372. Is it reasonable to assume that the variances are different? So in my line of work, if we see a greater variance, why would we be, I'm just as an empirical question, why would we be interested in differences of variances in two populations? Well, one thing is that if a course has a very large variance in the number of points that people get from the exam, or the way they have, is that we know that the people coming in probably have a different backgrounds. So this background meaning that they have or maybe taken different courses before that. Maybe they have a different kind of a ground education, the basic education or something like this. And then we can do something to make sure that the variance is not too large. So we can compare two courses. If they have they have different variances, then we know that the students coming into this other course are more homogeneous than the students coming into this other course. Let's switch to MATLAB again, and let's do this. We have this F distribution here. So it's F, yeah. Just let's switch to MATLAB. Okay, so we have already established the sample variances at 478 and 300, and so we have n equal 51. We have m equal 26, right? We have the S2A is 478, and S2B is 372, right? So as easy as it's this easy. So we calculate at F at S2A divided by S2B. So we get this F value at 1.2849, and we determine the critical region. The critical region, if we use the two tails, the critical regions would be, we can calculate these at let me just, it says reasonable to assume. So let's just take the reasonable to assume that we have we have two tails. We have the lower tail and we have the upper tail. So I'm going to just call it F low, no FL as the F inv, and now we have two. So I'm going to have the 0.025 n minus 1 m minus 1. So this is my low point. So if it's below this, then I would expect that the A has a smaller, because I was dividing the sample variance of A. So if it would below this, I would I would deduce that it's so low, the proportion that A has a lower variance, and then the high one, 25%, sorry, 2.5%, so that's 975. And then if it's above 2.0787, so I would say that then it's if it's above this, then the proportion is high. Now, do we conclude that these variances are different? So no, we do not conclude that. So let's calculate the p-value. We can calculate the p-values at FCDF of capital F at n minus 1, m minus 1. So we get that this probability is relatively high. So it's about 125. So it's the p-value is let me just double check. Oh, sorry, we have to calculate this. 1 minus that, and then because this is, no, we get the p-value is 0.5. So it's about 50-50 chance of getting a value that is either this big or this small. If this was a one-tailed test, we would have this p-value at 1 minus that, and would be 25%, but the p-value is still very large. So we conclude that these courses do not differ, at least not significantly. Right. So that's the last thing I have here. Yeah, so we've now reached the end of the material. Yeah, we're done. those are all the tests that you're going to be having. So let me just share that. So let's very quickly look at the tests. This week's topics. Understand the formulation of the hypothesis. I claim that the formulation of the hypothesis is more important than the particular test. I can provide you with the formulas for the tests, but what I can't provide you with is the ability to think in terms of this hypothesis formulation. And you postulate the null hypothesis, which is a conservative estimate. So for instance, if you're doing a medical study, you make the null hypothesis as that this drug is no different from placebo, or these two populations are not different, or something like this. Then you come up with the test statistics that should be roughly have a known distribution. In this case, in the expected value case, it's fairly easy because we come up with either N01 distributed or T distributed variable, depending on whether we know or don't know the variance. And if that turns out to have an extraordinarily small or extraordinarily large value, as determined by whatever our alpha is, in this case, the alpha, usually it's 5%, sometimes it's 1%, sometimes it's even 0.1%, depends on what we want for that. In some cases, they want it to be 1 in trillion, something like this. I know that's if you I don't know if you followed the news in science when they were looking for the Higgs boson. So what they wanted was a alpha level of ridiculously small. So assuming everything is just noise, then what is the probability of getting those measurements that you get if there is no Higgs boson in that? So they got the probability, the p-value was like 0.0000000000000000000000000000001 or something like this. And then they were confident in claiming that they had actually found it. So for the expected value, the testing hypothesis is very easy to formulate because you have the N01 variable. For testing the equality of two distributions, the equality of expected values, you test whether the difference of their expected values is 0, and then this only applied when we had the normal distribution assumption. Now, you have to understand that if again here, if these samples are large, this will be roughly normally distributed. So at the limit, it will have this normal distribution at the limit as n grows towards infinity. So this test statistics does work as n approaches infinity. But for relatively small n, it's a little bit problematic claiming that this test is a reasonable test if you don't have normality already present at the variables level. So all of these tests can be carried out with variables that we don't know to be normally distributed if they're regular enough so that we can assume that there is some kind of a reasonable average or a reasonable expected value. And if our n is large. But I urge you to look at these t distribution differences between t distribution and N01 distribution, and you notice that there is a marked difference when you talk about p-values of 0.05. So if n is small, then the t distribution is much wider. It has a much bigger uncertainty. So if you come up with the z variable like this with the N01 distribution, then you have to have strong grounds to assume that you know these variances. The problem, if you don't know the variances, then the only way you can get around it is by assuming that the variances are the same. And here's a trick. I mean, I said here that you have to assume that the variances are the same, but if you have a large sample, you can run the f-test to test for the sameness of variance. And if the f-test tells you that you can assume that they are the same, then assume they are the same. And if you have a large enough n, that works pretty fine. It's not a big deal. You can use this then as your test variable or test statistics for the, depending on, okay, that's a good question. So depending on the distribution, if you have your regular distribution, for instance, if you can assume that the distribution is a binomial distribution, for instance, then the n doesn't have to be very large. I mean, even 15 to 20 for binomial. So you have Bernoulli variables. Remember Bernoulli variables. So you carry out a test and the result is 0 or 1. So you get cancer or you don't get cancer. So if you have n equal to, let's say, about 15 or something, and the probability of getting cancer is somewhere in the region, mid-region, so it's not 0.0001. So if n times p is greater than 5, remember that was the rule of thumb. If you have a binomial distributed variable, or you know, if you have a Bernoulli variable and n times p is greater than 5 and n times 1 minus p is greater than 5, both of these apply, then your n is large enough and you can use the normal assumption, normal distribution. If it's a uniform distribution or something like this, then a usual rule of thumb is to assume that it's above 30. I think I've seen 32 is for some reason 32 is something that is considered large by many people. Over 30 as a sample size for distributions that are flat or, you know, have this bump but have some limits to them. Then there are pathological distributions, ones that stretch to infinity, to where that are not symmetric, that are always positive or something like this, but tend to converge to these humps and bumps and so forth. Then all bets are off. So, but if it's a reasonable thing like human height, then human height, for instance, tends to have this somewhat normal-like distribution. So if n is in the high 20s or 30s or something, then you are pretty safe at using it. If your sample is well picked and it doesn't have a really fat tail, meaning that like, for instance, let me give an example where it doesn't work very well even if n is large. Let's say you take rock and roll bands and try to say something about their average incomes. Then taking n equal to 30 or n equal to 20 might not give you much information, because there are millions, you know, literally there are thousands or tens of thousands of rock and roll bands, and only a handful of them ever make it. So here the probability of earning big bucks is very small compared to the number of people who are actually trying. So those kind of pathological distributions where there's a very heavy tail, very long tails in one end or the other, then those might be problematic. But your usually physical characteristics, variables that have physical characteristics like you know, height, weight, something like this, not susceptible to network effects and the Matthew effect, then n in the around of 30s is probably big enough. This is more of an art than science, really, in that sense. You have to look at the particulars of the variable that you're talking about. Yeah, I mean, did I answer your question? I probably didn't, but yeah, in the exercise, you can assume n is large enough, right? I always say that you assume that it's normally distributed in the exercises and the exam. I'm not going to ask you carry out I taught you these computations in the case where you can safely assume that things are normally distributed or n is large enough. However, I want to stress that it is in applications of this theory into the real world that you have to really stop and think, does this tool actually work? Is it really something that I can use? I have because I was using other people's material, I don't have a very good collection of examples where we get really bad results. But I really urge you to look at things like, well, Nassim Taleb's book, The Black Swan, is actually pretty good treatise, because in finance, they often use the ideas of normal distributed variables, normal distributions, or at the limit normal distributions, and so forth. And the infamous Black-Scholes model for option pricing and so forth, that relies on certain normality assumptions, but then, you know, it's not going to, the tail end of the distributions are much thicker than assumed in normal distribution. You know, the coronavirus already is an example of a situation where the tail end of the distribution is you know, things regarding the economy and things regarding where there are outside factors that you cannot contribute, other than normality assumptions probably don't apply. But if you have physical things happening, a machine drilling holes, or a machine filling bags, and there's a certain level of randomness there, then barring any catastrophic failure, if you can detect those and assume that the catastrophic failures don't happen, then usually things can be assumed normally distributed. But in the exercises, you always have to do this. I mean, I didn't provide you with any tools of computing this, and you know, many people think that we cannot control that sort of randomness, one that there cannot be controlled or contained into this this idea of using the central limit theorem. So for large enough n, things are normally distributed. If that doesn't apply, then we just don't have any mathematical tools. For variables for which the central limit theorem doesn't apply, we don't have tools now. Yeah, no worries. All right, any other questions? So, because I mean, next week I'll go through the material. On Friday, this is a very highly important. We don't have the time, I didn't have the time to go through all these examples in great detail today, but on Friday, we'll go through each of these questions, or each of these tests. We have an example of each of these tests, and we will cover them closely, and we will look at them, and I'll show you how to do those tests. I will provide you for it, you know, when you have the exam, and I'll provide you with the details next week for the exam, how it's done. But the idea is that you have all this material at your disposal, so you can use MATLAB or whatever and calculate things, and you have to write your kind of like a report, and you have few hours to do that. I haven't figured out the technical details, but it'll be on Moodle, how it's done, how the exam is done. So it will involve calculating certain probabilities, doing some statistical tests, and calculating some confidence intervals and that kind of thing. So please, I mean, maybe this week's example session on Friday will be one of the most important things that in this course, you know, because this is a culmination of what we've done. All right. Friday, it will be at 9 a.m. Yeah, I'll put it on Moodle, but it's 9 a.m. Right. Okay. Right. I think I'm going to stop the recording now. And you still have time for some questions, but we can stop if there's nothing else.